Good morning friends. Today we are going to see eigenvalues and eigenvectors. One of the important concepts of a matrix. Let's see content of this today's presentation. A definition of eigenvalues and eigenvectors. Next, eigenvalues. Separately we will see what is the meaning of eigenvalues. Second, eigenvectors, that is how to find eigenvectors for their corresponding eigenvalues. Next, properties of eigenvalues and eigenvectors and linearly independent eigenvectors is the today's presentation content. Let us move further. Definition. First, combinedly we will see the definition of eigenvalue and eigenvector. Let's try to define. Remember, a non-zero vector x is an eigenvector of a square matrix A if there exists a scalar lambda such that Ax is equal to lambda x. Then lambda is an eigenvalue of A. This is the simple definition of eigenvalue and eigenvector. They are related to each other. To the corresponding every eigenvalue there will be a eigenvector which is a non-zero vector. Clear this one. Note, zero vector cannot be an eigenvector even though a0 is equal to lambda 0, but lambda can be 0 eigenvalue. Maybe a lambda becomes 0, but eigenvector x, to say x is eigenvector, it should be not equal to 0, but lambda is equal to 0, the may be the eigenvalue for the matrix. Let us see an example for this. Suppose a matrix, suppose x is our eigenvector 2 1 for the matrix 2 minus 4 3 minus 6. Let's verify this whether it is correct or not. Ax we will consider, it becomes 0, the equation number 1. Suppose lambda is equal to 0 is eigenvalue, then the value of lambda x, that is RHS of the equation Ax is equal to lambda x. To multiplying 0 we get again a 0. Both LHS is equal to RHS. We can say that 2 1, that is x 2 1, a non-zero eigenvector, is an eigenvector for a zero eigenvalue lambda. For a zero eigenvalue, that is lambda is equal to 0, is the corresponding eigenvalue of a non-zero eigenvector 2 1. Okay, hope you understood. Simple. Lambda may be 0, but x, all elements of x will not be equal to 0. That is the meaning of a eigenvector. Now separately we will discuss what is eigenvalue and what is eigenvector. 100% they are related to each other. Okay, now separately try to define the eigenvalues. Let x be an eigenvector for a matrix A. Then there exists an eigenvalue, we can say scalar constant lambda, such that Ax is equal to lambda x, or equivalently we can say Ax minus lambda x is equal to 0. Take x common from the above step, we get A minus lambda x into x is equal to 0. Let's try to define the new matrix B A minus lambda. Then we get Bx is equal to 0. Bx is equal to 0. If B has an inverse, then x is equal to B inverse of 0 is equal to 0. Any matrix into B, it becomes a 0. But eigenvector cannot be a 0. Therefore, this shows that x is an eigenvector of A if and only if B does not have an inverse. Equivalently, determinant of B is equal to 0, or determinant of A minus lambda I is equal to 0. This is called the characteristic equation of A, and its roots determines the eigenvalues of A. If we found the determinant of A minus lambda I, you will get the required eigenvalues. A minus lambda I or lambda I minus A, we can consider. Both these cases are same. Okay, hope you understood. Let's move for the next slide, that is examples. First we consider eigenvalue of for the matrix 2 by 2. Suppose A is example number 1. Find the eigenvalues of A, where first row is 2 minus 12 and the second row is 1 minus 5. In previous slide we have seen A minus lambda I will be our characteristic equation, or A minus lambda I or lambda I minus A. Both are correct, no problem, because we are equating to 0. We can multiply simply by negative sign also. That is, lambda I means lambda is a scalar and I is a unit matrix of the same order as A, that is of 2 by 2. That means lambda, we have to subtract the diagonal elements of A from the lambda, that is lambda minus 2 and lambda minus 5, because minus 5 is there already, therefore it becomes a plus. That is our new matrix. Lambda I minus A determinant is lambda minus 2, 12 minus 1, lambda plus 5. We know that how to solve the 2 by 2 determinant. After solving this, that is cross multiplying, we get the polynomial as lambda square plus 3 lambda plus 2, that is 2 eigenvalues will get minus 1 and minus 2. The roots of characteristic equations can, these are the two different eigenvalues. Remember, eigenvalues are maybe 0, maybe negative, maybe positive, maybe fraction numbers. Okay. Another case is there, that is note the root of the characteristic equation may be repeated. Lambda is equal to lambda 1, lambda 2 is equal to lambda 3. If that happens, the eigenvalue is said to be a multiplicity of k, means its corresponding eigenvectors are repeated. It becomes k times multiplicity of the remaining eigenvalues. Now let us consider one example of repeated eigenvalue, that is of 2 by 2, 3 by 3. Consider second example. The first row is 2 1 0, second row is 0 2 0 0 0 2. If you observe, the type of the order of the matrix is 3 by 3, and it is a one special type of matrices, that is a triangular, upper triangular matrix. Below of the diagonal elements are 0 2 2 2, below of the diagonal element, that is 0 0 0. Okay, for upper triangular matrix, now we have to find the eigenvalues. If you found lambda I minus A, the value means what? Just subtract the diagonal elements of A from the lambda, we get lambda minus 2, lambda minus 2, lambda minus 2, remaining matrix as it is. After solving these, we get lambda minus 2 into lambda minus 2 into lambda minus 3, that is lambda minus 2 bracket cube is equal to 0. That means lambda is equal to 2 is an eigenvector, is an eigenvalue of multiplicity 3. That is 3 times a repeated eigenvalue 2 2 2. Okay, now we will move further for eigenvector. To each distinct eigenvalue of matrix A, there will be a corresponding at least one eigenvector, which can be found by solving appropriate set of homogeneous equations. If lambda I is an eigenvalue, then the corresponding eigenvector is xi is to be solution of A minus lambda I into capital I into xi is equal to 0. We will continue the above example for the same. Suppose lambda 2 by 2 matrix, lambda is equal to minus 1, then what is our equation? Lambda I minus A we have considered, that is minus 1 into I minus A. Just subtract diagonal elements of A from minus 1, we get as minus 3, minus 12, minus 1, minus 4, so that by using elementary transformation we can make the last first row 0, as it is a multiple of 3. Just subtracting, we get r1 upon 3 minus r2. If you did the transformation, we get 1 minus 4, 0, 0. After converting this matrix into equation forms, x1 minus 4 times x2 is equal to 0. Therefore, we have to consider one solution, that is x2 is equal to t, so that we will get x1 is equal to 4t. That is x1 is equal to x1 comma x2, small x1 x2, that is 4t. T take common, 4 1 will be our eigenvector. Similarly, we can define for lambda is equal to minus 2, we will get the eigenvector 3 1. Now let's consider eigenvectors for a 3 by 3 matrix where the eigenvalues are repeated and repeated 3 times. Similarly, again 2i minus a into x, because our 2 is our eigenvalue, we get the system as 0 minus 1 0. For this system we get x2 is equal to 0. For remaining values we have to consider its solution as x1 is equal to s and x3 is equal to t. For s and t, two both are not equal to 0 simultaneously. This is eigenvector for repeated eigenvalues. Now let's move further. Consider now properties of eigenvalues and eigenvectors. This is an important concept which is important for your GATE exam also, engineering GATE exam. Definition first, we'll see the trace of matrix means the sum of main diagonal elements. That is simple meaning for trace of a matrix. For any matrix, just addition of the diagonal elements a11 plus a22 plus a33 plus a44 and so on. This is called another name for that sum of the diagonal elements is trace of a matrix. Okay, now we will see one by one properties of eigenvalues. First we will see the properties of eigenvalues. First property is the sum of eigenvalues of a matrix is equal to trace of the matrix. That is means what it means, if suppose a matrix A having eigenvalues 1 2 3, then its addition will be 6, that is equal to its sum of its diagonal elements. That is the meaning of the first property. For previous example, 2 2 2 are the diagonal elements and its eigenvalues are 2 2 2 repeated again. Summation is 6 6 in both the cases. That is the eigenvalue and the relation between trace and eigenvalue. Next, the matrix is singular if and only if it has a 0 eigenvalue. If the determinant value is 0, that means we can say the matrix is singular. Then we can say that at least one eigenvalue of the matrix is 0. Understood? Suppose A is a matrix of 3 by 3, its determinant is 0, means what? At least one eigenvalue for that matrix is 0. This is the second property. And the third property is the eigenvalue of an upper or lower triangular matrix are elements of the main diagonal. It is easy, we have seen in the previous example. What is that? Upper triangular matrix is there, the eigenvalues are the diagonal elements, that is property 3, and it is valid 2 2 2. Okay, now next, fourth property, if lambda is an eigenvalue of A and A is invertible, then 1 upon lambda is the eigenvalue of the matrix inverse. What is the fourth property? Invertible means inverse should be exist, that is determinant not equal to 0. Then its eigenvalues is 1 upon lambda. Suppose A is our matrix, its eigenvalues are 1, 2, 3, then eigenvalues of A inverse are reciprocal of their respective eigenvalues, that is 1 upon 1, 1 upon 2 and 1 upon 3. This is the property for inverse matrix eigenvalues. Okay, now let's move further for the next property of eigenvalue. If lambda is eigenvalue of A, then k lambda is eigenvalue of the matrix Ka, where k is a arbitrary scalar. Easy. Suppose a matrix having eigenvalues 1, 2. Okay, and if you multiply some constant to the matrix, then matrix becomes Ka. Then its eigenvalues are again k into 1, k into 2. Suppose 2 is our factor, then 2, 4 will be the eigenvalue of 2 into the given matrix, that is the scalar number k. If you multiply some scalar to the matrix, it means that what will be its eigenvalues? Just multiply that k to the eigenvalues. Okay, if lambda is eigenvalue of A, then lambda raised to k is eigenvalue of A raised to k for any positive integer k. Okay, this is another property, easiest one. Okay, let's try to define some. Consider an example. For matrix A, the eigenvalues are 2, 3, 4. And if you suppose A raised to k, that is A square, if you consider the matrix, then eigenvalue for that matrix are square of the eigenvalues of A, that is 2 square, 3 square, 4 square, means 4, 9, 16 are the eigenvalues of A square. Directly we can consider the eigenvalues for the matrix. This is the property number 6. Now move for the property number 8. If lambda is eigenvalue of A, then lambda is eigenvalue of A raised to t. Clearly, suppose a matrix have A having eigenvalues 2, 3, then if we consider its transpose, A transpose, that is interchanging rows into column, if you find the eigenvalues for the same matrix transpose, we will get the same eigenvalues 2 and 3. This is the property number 8. Next, property number 9. The product of eigenvalues of the matrix equals to determinant value of the matrix. That is, suppose eigenvalues are 2 and 3, then the product is 6. Then its determinant value will be 6. That is the meaning of the property number 9. Product of eigenvalues is equal to determinant value. That is the simple meaning. 2 eigenvalues are there. That means the product is 8. It by default its determinant value of that matrix is 8. That is property number 9. Now linear independent eigenvectors we will see. Eigenvectors corresponding to distinct, that is different eigenvalues, are linearly independent. That is the theorem. And the second is, if the lambda is eigenvalue of multiplicity k of a n by n matrix of A, then the number of linearly independent eigenvectors of A associated with lambda is given by m, which is equal to n minus r. Furthermore, that the value of em lies between 1 to k. let's consider a matrix eigenvector of 2 are of the form, in this form, lambda is equal to 2 has 2 linearly independent eigenvectors. Okay, thank you.